this video and upload to the Blackboard later. So can anyone send a message to tell me you can hear my voice and see my screen? Yeah, thank you. So basically, based on different students' opinions and feedback, so we are now organize a new section exercise class and try to do a exercise and lead you to know more about the exercise class, and instead of just watching the video. And then the exercise class is about 30 to 45 minutes, and then later on the 15 or 30 minutes left, you can just ask whatever you want you don't know about this course and about GL knowledge. Yeah, so just we have merged the consultation hour and the exercise class. And during the consultation hour, I will turn off the recording and you can just feel free to ask whatever you want. So basically, I will just give an example you can see on the backboard. If you cannot see it, please tell me immediately. And yeah, here is exercise class 8 about the linearized gravity and gravitational wave. And so basically, this exercise class held by me, I would try to be more interactive. And yeah, I will let you guys to do the first part, A part, 1, 2, 3. I give you 5 minutes to do it, and then I will give you the answer. So, and then after we finish the part A, we will go for part B and part C. Part B 5 minutes, and then I will show you the answer. Part C 5 minutes, show you the answer. So make sure you can follow me properly. So let's start now. You have 5 minutes to do the part A. All right, time's up. So basically, the first part, if you learn the G-wave property, it will be very easy. Just know what is weak field equation and Lorentz gauge. So maybe in the lecture notes or in the first course, whatever you read, the procedure how to linearize a gravity is just basically all the symbol h mu nu, h bar mu nu, and different cases about the gauge transformation. So you maybe haven't seen a questions like I have a capital A mu nu with a proper matrix, and then we can use it as a very good example to show you how I can transform a h mu nu or h bar mu nu, whatever, to h bar mu nu Lorentz gauge, and then to use the T gauge and reduce all the degree of freedom to see h plus and h cross. All right. So we have an arbitrary weak field weak field metric a capital A mu nu. So we have such assumption. First, I have to copy this part. So that you can see my question when drawing the answer. So basically, for the first part, we have assumed the amplitude of the Minkowski metric is much larger than h eta mu nu, right? And we for the weak field perturbation, we have g mu nu is approximately equal to eta mu nu plus h mu nu, just the perturbation theory you have learned. And then we assume we drop all the term bigger than h square, the magnitude bigger than x square, and then we just remain one h in all of our answer. So for the A part, so that this wave satisfies the weak field equation. So what is the weak field equation? Basically, I haven't specified. If you are very well enough, you may ask me whatever I ask weak field equation in a vacuum or with source term. So basically, I haven't typed it in here in order to let you to ask me, but no one asked me. It's okay. So basically, I assume here the weak field equation occurs in vacuum. We calculate the gravitational wave in vacuum. So the weak field equation we have to satisfy is like h bar alpha, right, equals 0. You can see it in your lecture notes. So this is a weak field equation. So for our case, we have it. We have to test it whether it is equal to 0. So basically, you can easily to see it. And I gave you a hint that we can take the derivative as a k alpha by some complex analysis technique, just like EM. So in the EM field and EM wave, you can just basically take the lab del to replace it by the ik vector and also the time derivative to become the minus I omega. So is equivalence that we take the 1 alpha equal to k alpha. So and then we just plug it. For we can just expand all of it. You may wonder that why it's not G alpha mu instead why eta alpha mu instead of G alpha mu, because we drop all the OH2 term because we have to times a back H alpha. If we don't we use alpha mu, it would be a eta alpha mu plus H alpha mu. It would appear H alpha mu square term, and we have to eliminate it. And after that, after simplify that, we have a equation to show whether I make some typo. Okay, you have to calculate this for the part I, and then you will obtain some answer. So as I have gave you the hints about the K, right, of the 4 components of the K, you know that the K alpha, it must equal to 0. And what is the physics behind it? It is the null vector or null wave, which means we assume the graviton is equal to 0, just like photon case. And because this, if you have learned the 4011, the classical mechanics 2, the special relativity is just basically the PP equal to m c square, right? And something like that. Don't mind if I have wrongly make some mistake for the index. And the m we assume that it's 0, so we have low wave solution for it. And now we have which have checked it. We satisfy the big H mu nu, satisfy the wave field equation. And then part 2, whether it is satisfy the Lorentz gauge. So basically, the Lorentz gauge is just the derivatives of the A eta, okay, equals 0. So this is the Lorentz gauge. And make some typo. Oh, sorry, I make some typo. Here is the alpha. X mu nu alpha. Yeah, this is the weak field equation. Sorry about that. And this is the weak field equation. Yeah. So yeah, sometimes I mess up with the weak field equation and the Lorentz gauge. And then here is the Lorentz gauge. Whether the solution match the Lorentz gauge. After we expand of the Lorentz gauge to check whether it is satisfied, we expand it to be here. And then we find out the answer is very easy because we just plug in all we have of the KT, KZ, and all the component of A of mu T, because the A matrix is just like this, right? Okay. And then it will be equal to 0. So it satisfies the Lorentz gauge. Okay, weak field equation satisfied. And here is our very proper gravitational wave. And the part 3 is very easy. So it is whether it is symmetric and all the G mu nu, the metric is symmetric. So you can test it. Transpose is equal to itself. So after that, do you have any question about the part A? Please ask now. better use your mind to ask if
想
you
問
have
咧，嗰個你喺個 Whitfield equation D 佢出嚟個 solution，你係我碌翻落嗰個位係
呢度
係你嗰度係有一行係 eta alpha mu 跟住 round alpha round mu， 跟住後邊 h mu new 啊。
哦，都係
咁
寫錯啲 index 嘅啫，都冇所謂啊。跟住咧
即係我唔係 sure 佢 round alpha round mu， 我 D 佢嘅時候，咁我係 D 緊個 K 噶嘛，即係 KX 啊 ，sorry。
你直接代咗嗰個彎係個 K 就得啦，其實。
即係我諗個，OK。好啦。我想
其實你代咗
問
落去就係咁，係。
Whitfield equation 咧，咁我哋喺呢個 case，我哋當佢係 vacuum 嘅零啊。咁我想問嘅係佢個零係，其實我係諗去做好似有個 Gaussian surface 包住某一個位置，即係嗰個位置冇 source 就係零，定係點樣？因為如果佢有 disturbance 嘅話，一定冇可能，即係點樣都有個 gravitational source 嘅話。
係啊，你嘅意思就係而家有個 gravitational source 當 point source， 你喺一個差唔多無限遠嘅地方，跟住深刻我哋而家 test 呢個位嘅 h mu 係就係咁意思。咁
所以我個等於零，只不過係我 care 嘅位置冇 gravitational source。
yes。
咁如果
佢嘅意思係我哋 assume 呢嚿嘢嗱，佢揈出嚟嘅時候呢啲咁嘅嘢啦 ，strong field 嘅話咧 ，strong field limit 我哋一定要 care 佢。OK。咁去到一個位，佢自己 dam 到嗰嚿嘢somehow uniform 咗。去到呢個位，我哋就可以 make 呢個 approximation， 就係類似咁嘅意思。咁
如果譬如我 test 個 location 夠近嗰個 source 啦 ，OK， 可能係可能爭10公里咁先算啦 ，OK。但係咁我要 care 嗰個 source 嘅時候，我係要 care 到幾遠嘅 source 咧？定係純粹係睇佢個 effect 明唔明顯嘅啫？
基本上咧，你如果 test 真係你話10公里，我 let's say 有個 binary black hole 咁樣，你冇可能用 analytical 嘅方法嚟計到佢嘅 gravitational wave。但
即係 technical， 如果我寫條 solution， 我寫個 equation 出嚟，我係要寫埋個 t mu new。
因為我哋嘅 assumption， 你見到我哋嘅 assumption 就係一定係要呢個啊嘛，係嘛？如果你近嘅時候，你本身個 gravitational wave 就已經係有個 contribution of gravitational wave 喎。咩意思啊？即係本身個 gravitational wave 都有 energy。如果你喺呢個咁嘅 strong field limit 嘅時候，你 gravitational wave 會自己 generate gravitational wave 過你知開嘅。你 somehow 你 lecture notes 會知道㗎啦，呢樣嘢係咪？因為你本身 gravitational wave 係 carry 住 energy momentum 嘛。咁有 energy momentum 揈出嚟嘅嗰堆嘢就會有 gravitational wave， 咁就會無限延伸嘅，即係你呢嚿嘢係有 binary black hole 啦，佢 energy momentum 啊，佢會揈啲 gravitational wave， 係咪？咁你揈啲 gravitational wave 超勁嘅話，嗰堆 energy momentum 咪好高咯，嗰堆 gravitational wave， 呢堆 gravitational wave 亦都會揈翻啲 gravitational wave 出嚟，由呢堆又會揈，所以你係冇可能喺度做到任何 calculation。我答唔答到呢個問題？咁所以我哋去到最後啊，我哋 let's say 我總和晒所有嘢啦，我哋真係整低一個好廢嘅 gravitational wave 出嚟，我哋做一個咁嘅 assumption，eta mu 啲大過 h mu new，OK。咁我哋就去一個 so called weak field 嘅地方做呢個咁嘅嘢，做呢個 calculation。唔係你做唔到，呢個要用 numerical 方法先去做到。
咁如果我用 linearize 嗰個 equation， 但係 right hand side 唔等於0嘅，有啲咩情況會係咁？即係例如普通 Newtonian 嗰啲 limit。
你嘅意思係你嘅意思係有 source， 我哋而家係寫得個 source 嘅意思係嘛？
我好奇幾時需要寫低個 source， 幾時唔需要錄
？OK， 好問題。
因為有 perturbation 點樣都應該有個 source 有 perturbation 嘅話，我諗呢
係啦，啱啦。睇你嗰個情況係 assume 啲咩？其實，因為咧你 somehow 啦，你係想計埋嗰個 T mu new 嘅 contribution 咧，你都係可以做嘅呢樣嘢。即係你話我哋而家咧去到一個無限遠嘅地方，我哋當我哋已經 ignore 咗個 mass source 㗎，咁嘅情況嚟計，我哋而家呢條咁題目嘅啫。但係如果你話我真係 care 嗰嚿 T mu new 點樣變得唔得？然後再剔個最遠無限遠，咁我哋咪可以咁計咯。咁我哋咪要交 source 咯，啱啊。咁我哋嘅意思就係話，呢嚿嘢唔 vanish 咯，呢嚿嘢係點樣變，而影響我哋超級遠嘅 review 咁嘅意思。咁呢個時候你就要加個，咁呢嚿嘢就會係咁噶啦，係咪？
嗯。
咁你點計啊？咪 Green's function。咁 that's why 你 Johnny whatever 俾任何 lecture， 你個 problem set 裏面有條咪係 binary 乜乜乜嘅，然後你喺個地球度睇噶嘛之類嘅嘢啦，唔記得。係咪？咁你就係要用呢條式 Green's function， 然後你咪計啲 moment 啊，我唔知好似未教係咪？計啲 mass moment 啊 ，energy moment 咁樣 moment 嗰啲咁嘅嘢，即係 quadruple moment 啊，嚟計。So let's move on to the part B. We have to calculate. We apply a gauge transformation. A arbitrary Gaussian transformation B mu and times a sine wave and then we have the B mu have a 4 components such that we have a coordinate transformated H mu nu prime, and then this we assume this wave satisfy the TD gauge, the transverse traceless gauge condition. So you can try it now. I give you 4 minutes about it. Okay, I think time is up. Let me copy this question. Okay, let me tell you the answer. So basically, now we have do a general transformation, and we want to see what is the B mu and the A prime mu, such that we can make the H mu under a coordinate transformation, which is the gauge transformation that satisfies the T gauge. And basically, it's just what you have to do is just substitute all the component into substitute the Cassie mu into the equation, and then you can know it. It's very easy. Has eta mu one alpha Cassie alpha, and it's just the K alpha cosine K alpha. Yeah. So after that, you can find the A prime mu in terms of the all the other component. Okay, just a little bit calculation, and then how we just make it to satisfy the T gauge. First, for the traceness parts, we force it to be traceness. Okay, traceness. So we just consider the A prime mu, and the A prime mu traceness is just A prime mu is just basically equal to the A mu times A eta, which is the G mu, right? And we drop the H mu term, avoid the H square terms we don't want, and times the eta mu. Okay, so after that we know have A mu, and write out all of this. And you know the trace of a metric will be equal to 4. Okay. Finally, we can find something like that. And we make sure it is equal to 0. Set it equal to 0. Okay? And we find a new expression. Okay, we name it to be 1. And then for the transverse part, okay? Transverse part. So transverse part, basically you all have learned in the EM wave. It's just basically IGK equals 0, right? Which is the trace, just the transverse wave. And how we write into Einstein field notation, and how could I do it is very messy, right? But we have such condition, Lorentz gauge condition, right? Alpha equals 0, A mu alpha K alpha equals 0, right? Okay. We make use of the wave before the gauge transformation, which is the A mu alpha, right? And then we want this guy equals 0. How? We just need to prove the time component. The time component equals 0. The T alpha K alpha equals 0. And then we can just easy to show the Aij, Akj, Kj equals 0. And so we just calculate this guy, make it 0. And which we calculate the A prime t equal to A t mu and equal to finally we have a such condition. And after we all have derived this, calculate this, and then we have a eta component just minus alpha of 0, 0 equal to 0. And the mu component would be equal to 0. And then we have chasteness equal to 0. And then we finally, we can eliminate all the degree of freedom. We can find it is transverse. Okay, transverse way. And due to time limit, I can go for it, the part CD by myself. So basically, the part C is going to find A mu, A prime mu nu, and I should copy it. Basically, this is just all the calculation, and the part C find A prime mu nu. We know that this is the second equation. We make use 1. Okay, we know A mu plus 2 beta k mu equals 0, right? Based on the chasteness condition, we have to find a B mu. What is the B mu? And then we have to go to the A mu nu prime, and then we can find A mu nu prime. Yeah. And based on this is just basically very high school mathematics. Okay. B mu k mu equal to minus B plus C over 2. Why? Is because we have a copy the A mu nu, original A mu nu, just all the normal mathematics, and then based on use 2, the time component is all equal to 0, which means the TT, ATT minus something like that is equal to 0, AT set equals 0, etc. Yeah, as you have expected, a gravitational wave in the TT gauge, you may have TT mu nu just 0, 0, 0. All the other equal to 0. It just only have 4 components left on the center of the matrix. And then we have to calculate A prime XX and also A prime YY, which is the center component of the TT gauge after the TT gauge applied in the gravitational wave. So AXX, after some simple calculation, we know it equal to B plus alpha equal to B minus B plus C over 2. Yeah. And AYY is just AYY plus eta YY, B alpha K is equal to C minus B over 2. And then you can just put all the mathematics inside and Fine. Finally, we can know it is AXX, A, XY, AY, X, and AYY. And all the other components is equal to 0. This is general gauge transformation. In order to make it to be the TT gauge form gravitational wave. Only left B minus, yeah. So we adopt this gauge transformation with the C equal to B mu sine K alpha X alpha, right? We mix it, okay, arbitrary coordinate transformation. How the coordinate transform? The X mu, okay, become the X prime mu equal to the X mu minus or plus, as you want, a very infinitesimal small vector, okay, kasi mu, and then we transform this A mu nu to become the mu A prime mu to only have the, yeah, this is the plus minus. So finally, and part D is just going to find a new, sorry, I have prime here with a capital plus finally capital cross, because the H prime mu is just equal to H prime mu times the cosine wave, right? And then you just need to know, put the whole A prime mu to times the cosine wave, and then you have done all the question as do the matrix decomposition. Okay, very easy matrix decomposition. Okay, this is the H plus component. Here is the H cross component times the wave component. Finally, you can achieve something like this. All right, here, which is, yeah, done. So, any question about it? Okay, if no question about the very easy mathematics, I hope you can just learn about the physics behind it. Yeah, though I think I make very too much about exercise class. Okay, I close the recording.